Okay, so this is the very last section
Yay!
that we're going to cover in Chapter 10 and of this whole course, which is kind of exciting. Okay, now we are actually going to be spending 2 days on this. We're going to talk about all the concepts today and do some examples, of course, and then we're going to do some more. This is one that, just like 10-4, a couple days would be a good thing, okay? Now, notice the title is this time involving segments in circles, okay? Now, we've seen segments in circles already, but we've dealt with angles involving it, right?
Right, and mostly we've dealt just with the segment names, unless they were very specific types of segments.
So mainly we talked to, like, the last couple sections have been dealing with angles and arcs. Now, notice the title says segment lengths in circles. So there are some relationships when you have certain segments in a circle that's going to have some things happening. None of it's involving angles, which we could find angles and arcs, but it's specific to the length of the segments.
Man, aren't circles amazing?
Yes.
All these cool relationships, Miss Clara.
It's amazing. Okay, now notice these theorems, just like with angles, there's no theorem name, but it's more the concept behind it, okay? All right, so first of all, notice what they're giving you in this picture. I see two chords that are intersecting, okay? CD and AB are the two chords, and notice they're intersecting inside the circle, all right? Two chords could intersect on the circle, okay? But when they intersect inside, there's something kind of convenient about it. All right, it says then the product, okay, now we haven't seen this word in a while. Product, what does that mean?
When I'm multiplying.
Multiply the lengths of the segments of one chord. So you're multiplying the lengths of the segments of one chord. Now, what do you think I mean by that?
So, okay, I'm seeing that when they intersect, they're really, it's taking a chord and splitting it into two parts.
Okay, so like chord CD has CE and ED. Those are the parts that make up. Okay. Now, they're saying that product is equal to the product of the lengths of the segments of the other chord, okay? Because both of the chords are divided into two parts.
Okay.
Okay, now, are they divided equally?
Not necessarily.
Not necessarily. So be careful there. Unless we know it's actually at the center where they intersect, then yes, but most of the time they won't. All right, so let's jot down what this picture basically is essentially saying.
So it's saying that like CE times ED is equal to AE times EB. So the product of the segments of one chord is equal to the product of the segments of the other chord.
So as long as you know some of those pieces, then you could find some missing parts as well. All right, again, another equation, so some algebra is still going to be involved, okay? All right.
Okay, we've got some special segments, and you've seen some of these words before. We want to stress some of the vocab with some of this stuff too. When we talk about a tangent segment, it's a segment that is a tangent to a circle at an endpoint. So we've talked about tangent lines. And that we've talked about how sometimes within a tangent there are segments that we discuss. But an actual tangent segment is going to be a segment where we have a tangent to a circle at its endpoint. So looking at this picture down here, what do you think I would call a tangent segment?
Okay, well, I'm thinking, because I know tangent intersects a circle at one point, so I'm debating on, I see a segment PQ, but segment PQ is actually part of a secant, because if you contend it on, it intersects inside, so it's not going to be that one. So I'm thinking PS, and again, it has tangent to a circle at its endpoint, all right? So P is one of its endpoint, but it's actually intersecting the circle at point S. And if you continue that on, it's going to be part of a tangent line.
Right, and point S is that point of tangency of that line. Love it. Okay, now, a secant segment, again, we talked about secants before, and secants are parts of they are a line, but they intersect a circle at two places. Well, a secant segment is a segment that intersects a circle in 2 points with 1 point as an endpoint of the segment. So it's intersecting a circle in 2 points. That's important.
Which we know what secant lines are.
But 1 point is going to be an endpoint of the segment. So as you look here, the only other segment that I have on the circle.
Well, there's actually.
Well, there are.
The segment
the
PQ.
Parts.
QR can be considered a segment, but when you're talking about one of its endpoints is on the actual circle, that means you would have to be talking about segment PR.
Right.
Because I think sometimes people want to say segment QR.
And what is QR?
QR is actually a chord.
Right. So when we talk about a secant segment, we're talking about a segment that is part of a secant. So it does continue on, which chords have that same requirement, but this only has one endpoint on the circle.
The other endpoint, notice, is outside.
Yes.
So once you write PR up there real quick.
Oh, yeah, PR. And to do that too. Now, an external segment is part of a secant segment that's not inside of the circle.
Okay, so
All
that would have to be segment PQ.
So PQ,
it's part of that secant segment, and it's outside the circle because it's external.
right. So within a secant segment, you have the whole secant segment, but you also have just an external segment that's a part of that secant segment.
And guys, notice on this slide, the only segment that's not really talked about is segment QR, right? Because that is we call that a chord. That's a specific name. We already know it's a chord, so that is not something we need to define again. Now, these 3 words are going to be used for the next theorem, so just kind of be comfortable with that. All right, so the next theorem, notice these are kind of wordy, but I want you to kind of, again, notice it's going to start with kind of what are you given in the picture. So even when you look at this picture, based on what we just talked about on the last slide, I see some secant segments, and I also see some external. I do also have some chords, so we'll read about it. It says, if 2 secant segments share the same endpoint outside the circle. So in other words, these segments are intersecting outside the circle. So segment EB and segment ED is what they're talking about. So segment EB and segment ED. Now, when that happens, the product, we know multiplying, product of the length of one secant segment, so the length of one secant segment, and the length of its external segment. Okay, so the product, and again, product is multiplication.
So like I would be talking about
things.
like maybe EB times, so the whole length, times just the external part would be EA.
Okay, so I'm going to write that down. So EB times EA. So it's the secant times its external. This will equal, all right, the product of the length of the other secant segment and the length of its external segment.
Okay,
So it's going to equal.
it will equal the ED, the whole secant segment, times EC, which is its external segment.
Right now, I always like to write down because I love how Miss Hooker even said it. She's like taking the whole
secant segment,
whole secant. I'm going to even write the word whole times its external, and it's going to be the same on both sides of that equal sign. If you can remember that, when you have 2 secant segments intersecting outside the circle, this is what how you're going to set up your equation. All right.
Awesome. Now, you're going to notice that we've got a couple other theorems that really deal with the same kind of thing, or I should say just another theorem that deals with the same thing. It's just that now, instead of having 2 secant segments, notice I have a secant segment and a what?
It's a tangent segment.
It's a tangent segment. So when that happens, it's just a little bit different relationship because obviously I can't talk about when I've got a tangent segment
And an external.
It's external part because really it is just an external piece.
Mm-hmm.
And that kind of leads into this relationship. Mm-hmm. And it says, if a secant segment and a tangent segment share an endpoint outside the circle, again, the same criteria that they share that common endpoint.
So they're intersecting outside.
Then the product, so again, we're going to be multiplying, of the length of the secant segment and the length of its external segment. I'm seeing the exact same relationship there.
So far, it's, just like the last one. So you're taking the whole secant segment times its external segment.
That will equal the square of the length of the tangent segment. Mm-hmm. Now, I want to talk about this for a minute. So we're taking this tangent segment squared, which really means I'm taking it times what? Itself. Notice how this is, again, the whole secant segment and its external part. Mm-hmm. And we said, well, with a tangent segment, that really is the external part, is the whole tangent segment. So it's really taking that whole tangent segment times its external part, but they're the same thing.
Yeah.
So we're really just taking that quantity of AE and squaring it, saying that it's all of that stuff times itself.
So like this one, again, so you're taking the secant, the whole secant, times its external. And I like that you said that last time, so that's why I stressed that. Times the external, and that's going to equal your tangent squared. And again, it's really a product equal a product in a sense.
Right. And like I said, to me, I still think about it almost in my head like a segment, the whole segment and its external part. It's just that the external part is the same thing in this picture.
So you could write it squared.
Yeah.
All right, so let's try some examples. Now, again, one of the first things, just like when we were dealing with angles and circles, is think about what we're dealing with, what we're given. This time we're not talking about necessarily where the vertex is located. It's really what kind of segments do we have. So let's first notice, what are we dealing with in this picture?
We're dealing with two chords.
Two chords, or they could be considered essentially two secants because they intersect the circle at 2 points, but not a secant segment. I want to stress that, okay?
Well, and they're not lines. They don't continue on. We're looking
So,
for chords, yeah.
Chords is what we're dealing with here, okay? It says segment AB and CD are intersecting inside the circle. Find the value of X. All right, so what's the deal when you have two chords that intersect inside the circle?
That the product of the parts of one chord is equal to the product of the parts of the other chord.
Okay, so what's the parts of one chord?
So talking about like X and 18.
So I'm going to do what with
parts. I'm going to multiply those together.
So 18X
because those are the parts of chord AB, is going to equal the parts of the other chord CD, so 12 times 9.
Well, that seems easy enough. This is a
enough.
basic, real basic algebraic equation. So 100 or 18x equals
108. And divide by 18, X is 6.
Now, it said find the value of X. Have we done that?
We have found the value of X, so we're done.
Now, one thing I want to make a side note, just because I know on tests you might see something that takes it a little bit further. If the directions said find the value of segment BA.
Yeah, then I would have to, if that was the case, I'd have to add that 6 to the 18.
Which is not hard to do.
No,
But again,
just look at the
those directions. Okay, so just be careful with the directions.
All right, next one. Now in this picture, we're not dealing with two chords that are inside that are intersecting inside of a circle. What are we dealing with?
I see two secant segments.
All right. And there's a relationship that we know with secant segments too.
And I know that the secant segment times its external will equal secant segment times its external.
Right. And here what we're finding is segment HG, which that's the only piece when I'm looking at really just the parts. That's the only part that I don't know. Okay?
Which is actually a chord. It's not the secant segment.
You're right.
Okay.
So this is what I need to find.
Okay.
So how am I going to be able to do that?
Okay, so here's what I'm thinking. Because it's a secant, two secant segments that are intersecting outside, I know that it's the secant segment times its external. So I'm going to start with the one I have all the information about.
Okay.
And this whole secant is the FD. So that means I got to add the 10 and the 11, and I get 21. And I'm going to take that times its external, which is the 11, not the 10,
Right.
the 11, equals the whole secant segment. Now that is the HD. So if you could go over there to the picture real quick. The whole HD is the whole secant segment. Now here's where it's not as easy as the last one. I can just add 10 and 11. But I know that what makes up HD is HG and 12. So if I put HG plus 12, and I'm going to take that whole thing times its external, which is 12.
All right. So notice that Mrs. Palermo noted that you have to talk about the whole secant segment. It can't just be the part that we've got. That's just the external part. We need that, but we need the whole thing. So we need to add the segment, which is what we're looking for, to the 12 to get the whole thing.
And guys, you could label HG as X and say X plus 12.
Sure.
And just know that when you find X, you're actually answering the question, all right? It's kind of up to you,
Yeah.
all right? And if it helps to label the picture, Ms. Hochraby just communicated that whole thing. If you need to write HG plus 12 right next to that to kind of see that, you can do that as well.
Yeah.
Okay.
All right.
All right, so we're going to do a little solving, and I can do 21 times 11, and I get 231. And then over on the other side, I'm just going to distribute. So I'm going to distribute that through, so I get 12hg plus 144. And we can solve this. Subtract 144 from 231, and I get 87.
And divide it.
And then divide by 12. And this gives me not a whole number, but it does give me an exact decimal, so I can say 7.25.
Awesome. And that's what they asked us to find was HG.
Mm-hmm.
So
Now,
what you really found here was a chord.
Mm-hmm.
It wasn't really a part of, or it's a part of a secant segment, but it's not the whole secant segment or anything like that.
now, could you find the whole secant segment like HD
Sure.
first? Like, how would you set that up differently, like the equation, if I did that?
So if I had said, like, maybe if I had said this was all, I'm just using all of HG.
So you would say still 21 times 11, right?
Right. But then I would just say HD
Times the 12.
times 12.
And this would maybe not be as much work over that compared to that. However, it's not going to get you the answer directly, right?
Right. So then once you got your answer, you found all of HD, you'd subtract 12 from your answer.
So when you do that, you get 19.25.
And then you'd have to subtract the 12.
Uh-huh.
Okay. So yeah, good thing to point out because there are other ways of going about this problem.
All right, next one. The directions here says find the radius. Now, before we talk about what the radius is, what are you seeing in the picture?
I am seeing a tangent segment and a secant segment.
Okay, so we know there's a relationship.
And they are
going
intersecting outside the circle.
Mm-hmm.
And so that's good to know.
All right, so you have a tangent and a secant segment. Now, let's talk about this idea of a radius. What is a radius again?
A radius goes from the center to any point on the circle.
So it can go from here to here.
Right.
It could go from here to here. So I could say this is a radius, this is a radius.
Right.
Okay. So just something to kind of keep in mind. All right. Now, so going back, we have a tangent segment and a secant segment. So how are we going to set this up?
All right. Well, we know that the relationship with the whole secant segment and its external part.
Now, the whole secant segment is actually made up of the R, another R, and an 18. So we're going to add all those up, and I get
2R plus 18.
Now, be careful with that, okay? This is not the radius. This is actually the diameter. So you could say diameter plus 18, but it wouldn't get you directly to the answer.
I like the way that you've written that, too, because I think that that's a way it's going to be helpful for most people.
Okay, so you're going to take that whole secant segment. I'm going to put it in parentheses just because I know I'm multiplying it by
18.
And that's going to equal...
That's that external part. Equal that tangent segment squared.
Awesome.
All right.
All right, let's go ahead and solve it. So distribute. So I get
our 30...
Whoops. I meant to say 36.
36R. And 18 times 18 is going to give us 324. And 32 squared is 1,024.
All right, another just basic algebraic equation.
So if we subtract our 324 from both sides, we get 700. And when you divide by 36, we get a repeating decimal.
Okay.
So we could say it's approximately 19.44.
But there's no units.
There's no units.
And doesn't say round. So
we could turn that into a fraction and call that 19 4/9.
So just, again, same rules apply. If they don't have units, which they might have units on here, okay, then you could go ahead and round. Okay?
Right. So try to keep your answers as exact as possible.
Now, just a little kind of maybe, I know this is kind of off a little bit different beaten path, but this is going back to even the very first section. Do you remember, because radius is, you said distance from the center to any point on the circle, right?
Right.
So could I draw the radius to the point of tangency?
Absolutely. In fact, we know
And what happens when you do that?
that it's perpendicular to that tangent.
And so this is the radius as well. So you could set it up where you could use the Pythagorean theorem. So you could say, well, the hypotenuse, which is that one, which is r plus 18, that quantity squared.
Don't forget you'd have to FOIL that.
Equals r squared plus 32 squared. This will get you the same answer. It's just a different approach.
Yeah.
Okay? So that's what's kind of convenient about when you have a secant a secant and a tangent segments that intersect.
All right. For our next one, notice that we have the same kind of pieces, the same segments. We have a tangent segment and a secant segment, and they're intersecting outside of the circle.
Okay.
Okay, so let's talk about it. We want to find AC here, what is AC?
It is an external segment.
Yeah, so that's the piece that we're missing.
Okay.
Okay.
So I know that I'm taking the whole secant. All right. Now, I'm going to this time call AC X.
Okay.
So on the whole secant is the X and the 12 added together. And I'm going to multiply that by the external, which is X, equals your tangent squared, so 8 squared.
All right. Now, when we distribute here, I'm noticing that I'm going to be taking an X times another X.
Which is an X squared.
Oh, so this time we're going to have a quadratic.
Quadratic. So look, we've talked about them, guys. No worries. We can handle it.
Okay.
So it gets X squared plus 12X equals 64.
Now, when we've got a quadratic equation that has an X squared term as well as an X term, what are we going to have to do to be able to solve this?
We have to get it all equal to 0. So move everything to one side. And I think it'd just be easier to subtract that 64. And get it what we call standard form.
Right. Okay, we've talked about a couple different methods to solve an equation in standard form. I'll tell you guys that this is one that, let's see if we can factor it, because our leading coefficient's 1.
Yeah, let's try.
All right, so we'd be finding factors of
the negative 64. And it has to add up to a positive 12. Okay? So, like, I could start just randomly thinking of factors. Like 2 and 32. Okay? One of them has to be negative. So one of those negatives is not going to add up to 12.
No.
4 and 16, right?
Uh-huh.
If I make the 4 negative, because again, product has to be a negative here, I add those together, that's going to get 12.
So that will be the factor pair that'll work.
Okay.
There will only be one factor pair that works. All right.
So I'm going to go ahead and factor it. So it's going to be the quantity x minus 4 times the quantity x plus 16 equals 0. And then I just basically set each of those factors equals 0.
Awesome. And what do we end up with?
Well, the one on the left gets you 4, and the one on the right gets you negative 16. Now, here's what I'm thinking. Again, I found x, but did I actually answer the question? Let's go. It said, find AC, and I got 2 answers for x. What was x again representing?
X was AC.
Okay, so I'm thinking, all right, AC being 4 could work, all right? But I'm thinking AC being negative 16 can't work because you can't have a negative length, right?
Right.
So that one for sure does not work. So AC equals 4.
Just the 4. Love it. And yeah, most of the time in geometry when you get those negative solutions, most of the time they don't work if they're just representing that whole quantity of a segment or whatever. But what if this had been like an x plus 50?
Then it would have worked.
Sure, because if I add 50 to a negative 16, I'm going to end up with a positive segment length still, too.
And guys, checking it also, you could check it and say, okay, well, does 4 times 16 actually get you 8 squared? And it does.
Right.
Okay.
So a couple ways to check. So here we wrote x is 4. Let's write AC. Oh, sorry. Measure of AC is equal to 4.
All right, last one. All right, what are we seeing in this picture now?
I am seeing 2 secant segments.
All right, so we've done something like this already. All right, remember a secant segment, the whole secant segment times its external is going to be the same on the other side. Now, this one just says find x. So I know once I got x, I've answered the question.
Right.
All right, notice x actually represents what?
The external part of that secant segment.
All right, help me set this up.
Okay, so I know that the whole secant segment times its external part would equal another whole segment, secant segment times its external part. So let's say 15 plus 35. So I'm going to call that a 50 times our 15, its external part.
Again, the whole times its external.
Is going to equal our whole, which would be our 29 plus x, or x plus 29.
Either way works.
Times just the external part, which is another x.
Again, you can put it here. Miss Hograby, I know, noticed on the last one she put out front, because that's a lot of times how you'll see it written.
Right.
All right, let's go ahead and simplify down what we can.
Okay, so 50 times 15 is going to give us 750. And we're going to end up with an x squared plus a 29x. And I notice I do have an quadratic equation, but it's not in standard form. So let's move our 750 over.
Good.
So 0 equals our x squared plus 29x minus 750. Now, I'm looking at this as one, Mrs. Palermo, and I'm thinking, I don't know if I want to try to find factors of 750. I don't know that there's necessarily a factor pair that does work or not, but I'm not thinking I want to go there.
Well, because 750 has probably
Lots
lots of
of
them,
factors.
and it might take longer just to find them. And then what if you can't find one? So then another option, which we haven't shown, which is this is a great opportunity to show you, is to use the
quadratic formula.
Now the quadratic formula. All right, as a reminder, okay, it finds the value of x in a quadratic. It is the
negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm looking at this one. I noticed that the a is 1.
Okay, so I'm going to write over here. The a is 1, and again, it's the coefficient of x squared.
The b is 29.
Coefficient of x.
And the c is negative 750.
So I just have to substitute into that formula, right?
Right.
Now, when it says the negative b, that's essentially saying the opposite of b.
So here I want to use a negative 29 plus or minus the square root of, I'm going to take 29 squared.
Now be careful when it's negative, make sure you either put it in parentheses or just remember a negative times a negative is a positive.
Yeah, really that term right there, because you're squaring it, should always end up being positive.
Yes.
So there's my b squared minus 4 times my a was 1 and my c was negative 750. All of this is over 2 times my a, which was 1.
And keep in mind, if the a is not 1, you still have to multiply it by 2. Don't just put it over 2. Okay, that's a common mistake I'll see in algebra. All right, so now what do we got to do?
Okay, so let's simplify. We've got our negative 29.
And what do you mean by simplify, focus on underneath the radical, right?
Underneath the radical, yes.
So you could just type it all in your calculator.
Sure. In fact, I'll go ahead and do that. So 29 squared minus 4 times 1 times negative 750. And we end up with a 3,841.
And
then over 2. Now, we need to take the square root of 3,841. And we end up with a decimal.
Okay, so this is probably a good thing we didn't try factoring. Because, guys, if this number here underneath the radical is a perfect square, then you could have factored. If it's not, then the quadratic formula really is our best option. So we chose wisely here.
All right, well, good. I'm glad I didn't want to find factors of negative 750.
Okay, so here's the deal. So she typed this in our calculator here, and you end up with a rounded answer. I'm going to write that down just so you can kind of see it. Now, keep in mind, you don't want to round too soon and then use that to round again. So leave it in your calculator or just retype this again, okay? Maybe retype it over again. That's what a lot of times I do.
That's what I do too.
Right?
Usually.
So let's do it that way. Look, because I think we both kind of do that. So it's saying plus this amount, right?
Right.
I'm just going to separate this out. But it also is saying take minus that amount.
Now,
all over 2.
I'm just noticing something, Mrs. Palermo, that this, when I take the square root of 3,841, it's like 60, almost 62.
Okay.
Okay. If I take a negative 29 and I add that almost 62 to it, that's going to end up being positive, and I divide by 2.
Okay. And
that will keep it positive.
Okay.
But if I look at that second scenario, and I see that I'm taking a negative 29 and then I'm subtracting almost 62 from it, that's negative. And dividing by a positive 2 keeps that negative. And I notice that x is representing a side length. So I know I'm going to only have one possible value of x. Some of you guys may have that reasoning in your brain to be able to do that. If not, you can find the 2 answers and you're still going to notice that one won't work.
And guys, be careful though, because just because this says minus, sometimes this number here is a positive, and if you take a positive minus, it might be a smaller amount. It still would work. I always would suggest try get both of those answers just to see, and then just decide, because sometimes they might both work too.
Right.
Okay. So
and the only reason I'm coming up with that conclusion is because I've typed that
radical
in my calculator, and I know it's about 62.
Okay, so Ms. Hograber, we're going to type in negative 29 plus the square root of that, divide by 2. You get about
16.49.
And guys, you're going to have to round on these. These are ones we're okay. If you have to use the quadratic formula, you're going to have to round. All right, and then when you type this one, this ends up being about a negative
45.49, which there's no way we can have a segment length that's that
and
negative.
since x represents a segment length, this is the only value that will work.